Today we're going to be starting chapter 8. Chapter 8 deals primarily with being able to graph these functions, so sine and cosine, the other trigonometric functions. Now, if you are the kind of person who is not an enjoyable fan of graphing these functions when it comes to algebra, there's a few distinct differences I want to reference first. Number one, algebra is kind of sporadic and random. There's very few rules. It's almost the Wild West of functions. You can try to pick some random values and hope they work out, and sometimes they do, sometimes they don't. Trig functions, on the other hand, follow a consistent set of rules and guidelines. You can follow the same basic 5 steps and graph any trig function as long as you A, understand the steps, and B, know how the functions act, which is what we're going to focus on for these first couple weeks. It's focusing on how these functions look, how they act, and properties about them that are very important. So to start with, let's talk about some basic facts before we try to graph this thing. Now, I pulled these directly from the unit circle. We have, from the unit circle, the sine values, remember, are your y values. And we're going around, I'm using the radians in this case. You could do something similar with the degrees. I'm not a fan, just because with the degree values, they're a lot less common, they're a lot less noticed, they tend to be the lower numbers. So, let's talk about these functions and their basic facts. Basic fact number 1, we discussed last week. I'll make some small lists here. The sine function and the cosine function. We discussed last chapter their domains and ranges. So for the sine function, the domain was all real numbers from negative infinity to positive infinity. The range from negative 1 to 1, inclusive, meaning that the top y value was positive 1, the bottom y value was negative 1. For cosine, exact same thing. So at their start, you'll notice that they are very similar, which is actually a theme that will continue as we go through this listing. The range, same thing. The lowest value is negative 1, inclusive. The highest value, positive 1. Also from last chapter, we discussed how these are either odd or even. Sine is an odd function. And as a reminder, when it comes to odd functions, this means that it will be rotated around the origin. Whereas the cosine function is an even function. As a reminder from last chapter, even functions are those that reflect across the y-axis. Meaning you can fold them in half and they match up perfectly. With these basic facts, we're going to attempt to construct what these functions look like. Now, as part of today, we're going to have a mixture of some graphing components and some terminology. Now, like I said, you may be a type of person who does not particularly enjoy graphing functions. I understand. You would be surprised at how much math teachers hate graphing functions too. For the primary fact that for many functions, they are random. You're picking random numbers, you're plugging them in, hoping for the best. That's not how I want to live my life. Especially when math is supposed to be so concrete and precise. Picking random things just feels wrong. With trig functions, those rules do not happen. Instead, we'll develop, over the course of next time, a couple of key steps we can follow through every single time. That as long as we know this information, we can graph any trigonometric function or any change to a trigonometric function. And those will be the things we're going to talk about. Now, last thing I want to mention, the last factor applies to both of these, and it's a definition. These are what we refer to as, is above or below? So, perfect. These are what we refer to as periodic functions. Periodic functions are functions that, by definition, repeat the same pattern after a shift. Specifically horizontally, meaning left to right. Meaning that if I can draw one piece of this function, it's just going to keep repeating that piece over and over again in some form. And that piece we'll refer to as a period here in a second. That's why they're referred to as periodic functions. Where the thing that repeats is the period of the function. So, with these basic facts and our knowledge pulled directly from the unit circle, we will begin to develop our first pictures of these functions drawn by hand. Now, throughout, we're obviously not stupid. We have calculators. We have computers. We can draw pieces of these with the computer and with the calculator. I'm going to use that to help us at the end. But as I said before, all trig classes contain these two components. You have to be able to do some pieces by hand and some pieces with the calculator and computer. So I'm going to show you how to do the parts by hand that we need to know how to do, and how to prioritize those pieces so you can get them well and easily. Okay? Any questions about our basic facts? All of this stuff, with the exception of this new definition, is actually from last chapter. So again, these values pulled directly from the unit circle. You'll notice the unit circle is no longer up. Told you we need to start having it memorized, so I gave some advice to people to start working on it.
Do I need that chart on here?
This chart, I'm going to pull some pieces of to do my graphing. I'm not going to pull all of them because some of these values are not nice, you'll notice. But I will use pieces of this chart. So I just want to make sure you can see the entire chart, and I'll tell you what pieces I'm going to use afterwards. So those will be the pieces you want to put down on your paper. Okay? You might guess are the ones that have started.
Yeah.
Okay, so this comes from the unit circle from last chapter. This comes from our definition of domain and range from last chapter. Odd and even functions come from last chapter. This is the only thing that's new. And again, this should make sense because sine and cosine repeat because the unit circle repeats as you keep going around it. So again, it's about a repeated pattern. So what we're going to do, we're going to take our first look at what the sine function looks like. I'm going to do so by pulling out some specific values and graphing those values and kind of getting everything else to kind of flow in between. Not perfect, but a good estimation for how it looks. Now, I will do this 3 times. Once, referencing the top piece only, very broad general picture. I'll then use the fact that it's odd or even to draw more picture, and then I'll finally finish by using the fact that it's periodic to draw the full version of this function. So what you'll see is I'm going to draw 3 different sine pictures. One, the very basic, pulled from the unit circle. One, using this odd fact to add to it. And then finally, using the fact that it's periodic to draw the full sine function. So again, 3 times. The last one is the actual answer. But I want to show where it comes from. It comes from these 3 pieces. The unit circle, the fact that it's odd or even, and the fact that it's periodic. Here we go. I'm going to start. Sine function. I'm going to call this version 1. Ready? I'm going to take 3 of these values. At 0, the y value is 0. At pi over 2, the y value is 1. At pi, the y value is 0. Now, in algebra, you were probably taught to do things in a very specific way. Trig likes to do things that make sense, not the way algebra did them. So I will draw this, not by counting 1, 2, 3, 4, but by counting by the numbers that make sense with trig. Counting by pi over 2s in this case. So example, my lowest number is going to be at -1, because that's the lowest possible number I can get for sine. My highest number is going to be a +1. With this line right in the middle. Okay. So what happens? At an x value of 0, the sine value, so the y value, is also 0. It would end up right there. At a value of pi over 2, which I'm going to put right here, pi over 2, the sine value is +1. So right there. And then at pi, it's back to here. We will start here, and I will explain as we come back from lunch. We'll take a pause. Let's go lunch. Okay. So, we're about to finish version 1. This is pulling from the first 2 quadrants of the unit circle. I'll finish by A, putting my points down. This first point takes place at 0, 0. The second point is at pi over 2, comma 1. Again, Coding for the unit circle, pi over 2 is my x value, my angle value, whereas 1 is my output. And then finally, we have pi 0. With that, I can start to make a rough start of the sketch. Making those two almost like a half circle. Turns out this is not too far off from what it actually looks like. But let's continue. So this is version 1, where I'm just using the top information. That's it. Nothing else. In my secondary version, I'm going to pull in my next fact that I want to use, the fact that this function is odd. So I'm going to make another copy of this function, down below here, where we use the fact that it's odd to add more information into this picture. I'll then do my third version by using the fact that it's a periodic function. And you'll see that all of these have the same pieces in them. But in the end, it'll end up with an infinitely long function with a full domain from negative infinity to positive infinity that is bounded between -1 and +1 on top and bottom. All right. Version 2. Here we go. Now, to do version 2 and version 3, I'm going to go back to how we normally do it in algebra, where the y-axis is centered. Here we go. There's my y-axis. That's awful. Let's try that one more time. That's better. All right, roughly in the center. Here we go. Okay, I have a top value, +1, a bottom value, -1. So I'll put those 3 points just like previously we had. 0, 0 at pi over 2, 1, and at pi 0. So again, this side stays exactly the same, no difference. But now I'm going to use the fact that this is an even function to create what I'm going to call version 2. Oh, sorry, the fact that it's an odd function. Sorry. Odd function. We're going to rotate this around the origin. Now, as a reminder, rotating around the origin means that if on the right side it's up, on the left side it's going to be down. It's the exact opposite on the other side. So what this is going to do is, again, my 3 points, this one is at 0, 0. This one is at pi over 2, 1. This one is at pi 0. What it's going to do is it's going to create 3 more points on the left-hand side having the opposite properties. Meaning it initially goes up, now it's initially going to go down. So over here, at negative pi over 2, we're going to get down to -1. So negative pi over 2, -1. And at negative pi, I end up back on the axis, creating this odd function. Just a reminder, odd functions are ones that are revolved around the origin. They have this matching component around the origin itself. Now, to finish, I'm going to use the last fact that this is periodic to make my version 3. This is my full sine function. This is the first time you will have graphed a sine function completely by hand. Now, to let you know, for this class, we rarely care about the full sine function because it's periodic, there's a lot of repetition. So we'll focus mainly on one part of it at a time. But it's important to see what this thing looks like from the full picture. Here we go. Version 3. So, what I'm going to do now is, periodic functions, remember, repeat themselves after a set amount of space, called the period. In this case, this is going to be the period. I'm going to repeat this picture to the left, repeat that picture to the right, draw little arrows indicating that it keeps going. It's going to create a wave effect with this particular function, which we call, again, a periodic function. Here we go. Version 3. The final version. The director's cut. All right. We've got our center line right here. Booyah. Top of 1, bottom, -1. All right, here we go. So at 0, 0, at pi over 2, at pi, at 3 pi over 2, at 2 pi. Going to the left, same pieces. -pi over 2, -pi, -3 pi over 2, and -2 pi. So, let's see what we have. It starts, goes up to 1, down to 0. It'll go down to -1 and back up. Left-hand side, exact opposite. Goes down, comes back up to 0, comes back up to -1, comes back to 0. And with that, we create our first full sine function. This is a function that has the following properties. From 0 to pi, it matches the unit circle. It is an odd function, and it is periodic because it repeats itself over and over again. And in a second, I'm going to pull up Desmos. This is what this function looks like. That's exactly what it should. Now, as you can see here, this function will repeat itself multiple times. So what I'm going to do is I'm going to section off what I refer to as the main period of the sine function, meaning the piece that everybody focused upon when they learned about trig. Since all the pieces are the same, you can break this almost anywhere and it'd be fine. But this is the main piece everybody talks about. Right over here in green. This piece is our main or first period. We will spend the majority of this class, when we talk about the sine function, we'll focus on that piece of the sine function. Remember, the other pieces are just going to be duplicates of. If you look up on the wall, I added some information up there. One of them is the sine function, and you'll notice that the sine function matches this piece of the sine function. Because again, there's multiple versions of it, because I could have any piece of this be the sine function. I could talk about, this piece, or this piece, or this piece. I could talk about any piece of this. I'm choosing to focus on this one as the main one. Andrew?
Well, I was just going to ask if there was a reason that was the first period, or did you choose?
It's the first main one because of how it begins. The unit circle starts at 0 and goes upwards or goes downwards from there. So our first period starts at 0 and continues forward. That's the best reason I've heard it. It could just be that somebody decided that that's kind of the way they wanted to do it. It's hard to tell. Trig is actually older than almost every other math thing you've learned. Now, the graphing part of it's newer, but the rest of it, it's pretty old. So, this is our third version, our final version. Other than this, the thing just repeats over and over and over again. The same function, multiple times, a periodic function. I'll pull up Desmos so you can see the official one. Much cleaner than mine, but still not bad. And might I say, congratulations on graphing your first trig function. So notice it's the same properties we talked about here with sine. Okay, it starts at 0, climbs up to pi over 2, 1, descends back at pi to 0, falls down at 3 pi over 2 to -1, and then comes back up at 2 pi to 0. And again, that's the main portion we're going to talk about. That first main period. And everything else is just a copy of that picture. That's why it's periodic. So, this is the sine function as defined from last chapter, now put into a graph. It defines it with a unit circle, with the fact that it's odd, and with the fact that it's periodic, we create this picture. Questions about the sine function? Now, in the future, what we're going to talk about is, well, this doesn't represent everything. Maybe we talk about a sound wave in this class, representing some obscure guitar solo. That sound wave won't match this picture, but it will have pieces of this picture. Maybe it'll be taller, it'll be shorter, maybe it'll be shifted a little left, a little right. There'll be something different about it. But at its core, it'll act like this function does. Let's now look at cosine. We're going to build cosine the same basic way that we built the sine function, but with its properties instead. So cosine, instead of starting at 0, is going to start at the y value of 1. At pi over 2, it's going to drop to 0. At pi, it's going to drop farther down to -1. We're then going to use the fact that it's even to reflect it across the y-axis in our second version. And then we'll combine that with the fact that it's periodic to make our full version and talk about its main period that we'll discuss for the remainder of the class. Here we go. Exciting times. Okay. Version 1. Pulled directly from the unit circle. So, since it's from the unit circle, I'm just going to focus on the right-hand side. Left-hand side is not very important right now. I'll come back to that in version 2. So the top value is at positive 1. The bottom value is at negative 1. And the 3 values I have marked are at 0, pi over 2, and pi. All right, mark them up. First one. At 0, the cosine function has a value of 1. So at 0, the cosine is 1. At pi over 2, the cosine function has a value of 0. So I come up here at pi over 2, the cosine function has a value of 0, pi over 2, 0. At pi, has a value of negative 1. I come over here, at pi, the value is negative 1. So I can see it's going to make this rough picture. Notice I'm not drawing a straight path because, well, I have some experience with this, but because these values aren't really linear, they're kind of sporadically changing. And so I make sure I reflect that when I draw this picture. I get a little goose coming out, a little bump, a little bump. But this comes directly from the first 2 quadrants of the unit circle. That's version 1. Our initial choices. Let's look at version 2. I'm going to use the fact that it's even to finish this piece of the function. Now, because it is even, reminder, even functions are those that are reflected across the y-axis. What that means is, if it's to the right, it's going to match to the left. So let's talk about version 2. Here's version 2. So now, I'm going to, again, put this more centered. Okay. Top value is at 1. Bottom value is at negative 1. All right. Put them in. At 0, it's 1. At pi over 2, it's 0. At pi, it's negative 1. So there's that piece. Like that. But now, it's even. Even, remember, reflects across the y-axis. So if it's on the left-hand side, it's going to match the right-hand side. If it's on the right-hand side, it's going to match the left-hand side. What that means is, this pi over 2 is going to match exactly the same at negative pi over 2. The exact same spot, reflected across. At pi is going to match to negative pi. This is what makes this an even function. It should match left to right and right to left. Again, even function. Now, in my final form, I have over 9,000. I'm going to take this function, I'm going to make it periodic, just like it should be. I'm going to repeat this motif multiple times, once in each direction. Creating one function that meets all the properties of the unit circle, the fact that it's even and periodic. Here we go. Version 3. All right. Let me search space here. All the way over. Beautiful. Okay. So, top value of positive 1, bottom value of negative 1. Okay. To the right. Dot. Yeah. Pi over 2. Dot. Pi. Dot. 3 pi over 2. Going to repeat the pattern, going back up. And at 2 pi, we come back up here. So 2 pi, right there. There we go. And to the left, at negative pi over 2. At negative pi. That's negative 3 pi over 2. And negative 2 pi. And then, of course, it's going to continue. So, it follows our course as defined by the unit circle. It is even, so it reflects across the y-axis. It is periodic. This is our official cosine function. Now, as with the previous one, and for much the same reasons Andrew discussed a moment ago, we're going to focus on one piece of this, because the rest are duplicates, right? If we can isolate one piece of this, all the rest are just going to be copies. And for the same reason we chose from 0 to 2 pi for the first one, being the first part of the unit circle, we're going to make that same choice over here. For this green box, we're going to try to use it to define everything. It's going to be our first or main period. Again, reason why, it matches the unit circle. The unit circle typically starts at 0 and ends at 2 pi. So our first period typically starts at 0 and ends at 2 pi. Because again, with this piece, I can copy this picture and get this piece. I can copy it again and get the next piece. I can copy it again and get another piece over. They're all the same pictures because it is periodic. You notice now, I have taken those main or first periods and placed them on the grid. With the terminology we're going to talk about here. The sine function starts at 0, climbs up to 1, back to 0, down to negative 1, back up to 0. Make this nice wave form. The cosine function, again, starts at 1, falls down to negative 1, comes back up to positive 1. And with that, we can modify everything else around it. To finish today, I want to first show you guys this does in fact match the cosine function as defined by Desmos. And then I'm going to finish by looking at some more terminology to prep us for tomorrow. As you can see, there's some terms up there we haven't talked about yet. They'll be very important starting tomorrow. But for today, this is the main part of the notes done besides some definitions. Go ahead. Let's first verify Desmos. Don't let me down now. Goodbye sine. Hello cosine. Look at that. Notice that the cosine function is, in fact, periodical. It's the same picture, copied multiple times. It is reflecting across the y-axis, so it is even. Again, the left-hand side does match the right-hand side. And you can see all those values we talked about being values of importance. Okay. To finish today, I have 5 terms that we'll need to finish today. 5 definitions. Now, each one of these is going to be a way we can modify these two trig functions. Because sine by itself is, well, it's cool, but it's not enough. You know, not every earthquake is going to follow just the standard sine equation. It's going to be modified in some way. Not every sound is going to follow the sine equation, the cosine equation. It's going to be modified somehow. And so those modifications become the focal point. But you can't talk about the modifications until you know and understand that this is cosine. This is what it looks like. This is how it acts. This is where the first period of cosine is and how it acts. So, to finish, some definitions. The first one is a big and fancy word. It's my favorite word of this chapter because everybody wanted to complain about it. The word sinusoidal. Sinusoidal. It's not sinusoidal. If you say sinusoidal, I think you're talking about some kind of Peanuts character. Come on, sinusoidal. We want to go out and play. No. Sinusoidal. It means any function that acts like the sine or cosine function. Notice it covers both. Because sine and cosine are very, very similar. In fact, if you look at the two pictures next to each other, they're virtually identical with a small change. So a sinusoidal is any function that acts like sine or cosine. And that will be the focus for this week. We'll be talking about the sine function, we'll be talking about the cosine function, and versions of it that have been modified. They all fit in the broad category of sinusoidal. So that's the big one. That's the annoying one. This is the overarching theme for this week. Sinusoidal functions. Functions that are defined by looking or acting like sine or cosine. So, the way water moves is a sinusoidal function. The way sound moves through the air, a sinusoidal function. Photons of light, sinusoidal functions. If they look or act like sine or cosine, they're considered the broad category of sinusoidal. Basically, does, one of these. Sinusoidal. Okay. Our last couple of words are actually already on there, but they're not defined on there. They're in a picture form, so you can kind of see how they relate to the picture itself. So let's talk about those. Can I move on from here, or do I need to stay here for a few more seconds? Okay, I'll move on. So, these terms, I wanted to write down and make sure I didn't mess any of them up. I usually do. All right, here they are. Period, amplitude, midline, phase shift. These are different ways that the sine and cosine function, and eventually the other trig functions too, can be modified. You can modify the length of the repeated portion. So make the repeated portion stretch out or condense down. You can change the height of the repeated portion, called the amplitude. If you're a music person, amplitude, amps, they're related to each other. The higher the amplitude, the higher the amps, the louder the music is. The midline is the center or vertical shift of the repeated portion, how much has been moved up or how much has been moved down from the center of the graph. So if it is normally centered on the x-axis, it's up from the center, we'd say it has a higher midline. If it's below the center, we'd say it has a lower midline. And then phase shift. This is a change in the starting place of the repeated portion, so it's been moved left or right. So again, normally everything starts at 0 and lasts for 2 pi and has a height of 1. But we could shrink it, we could make it taller, we could move it a little to the left, we could move it a little to the right, we could move it a little up, we could move it a little down. All of these are changes we can make to our two basic trig functions, sine and cosine. And we're going to talk about some formulas tomorrow, how to make those changes happen, and make them predictable. So unlike with polynomials and quadratics, how they can feel almost random with how you find their values and graph them, these are meant to be predictable by these formulas. This is it for today. Our last 4 words. When you have them down, you are done. Tomorrow I will post a homework assignment because we have not actually gotten to the main. This is just the piece you need to know before you can start. Tomorrow we'll look at how the amplitude, period, phase shift just change the look of the functions and keep them sinusoidal. That is our focus for tomorrow. It's the beginning of the week. That's it. Any questions about what we talked about today? Okay. And to see an alternate version on the wall, you'll see that each of these terms is put in terms of the picture of that first period. So you can see how the period is how long that first length is. The amplitude is how tall that first length is. The midline is where the center of that length is. The phase shift is how far it's moved left or right. We'll go into more detail into that tomorrow, along with the formulas that go with it. That's it.